Okay, so we're going to go ahead and wrap our lesson up on 11-4. We have one more example to work on with the comparison test, and then we're going to introduce our next test, which is the limit comparison test that we can also use to test for convergence or divergence of a series. So the example that I had you guys work on to wrap class up last time was the sum from n is equal to 1 to infinity of 1 over the square root of n cubed plus 3. So again, this series that we are given most closely resembles the p series, 1 over the square root of n cubed, or n to the 3/2 power. So based on that, my prediction is going to be that this series here converges. Okay, so the given series is going to be our a sub n. So that's going to be 1 over the square root of n cubed plus 3. We're going to compare that to a b sub n, where we want b sub n to be greater than or equal to a sub n. And b sub n has to be a series that we can show hopefully converging using the p-series test or geometric series test usually. So I think the series to compare this to is 1 over n to the 3/2 power. And b sub n is going to be larger because both numerators are the same. The denominator for b sub n is smaller, thereby making the fraction bigger. Okay, so we have an a sub n that is less than or equal to b sub n, so we just want to write up our justification now. So since a sub n is less than or equal to b sub n, and the series b sub n converges by the p-series test, then our given series, which is the sum from 1 to infinity of 1 over the square root of n cubed plus 3, converges by the comparison test. And again, the only thing you have to be careful of when using the comparison test is that the terms of your series are greater than or equal to 0. If they're not, you have to resort to using one of the other tests that we've looked at so far in chapter 11. Okay, so that's the last example we're going to do with the comparison test. We're going to move on to the limit comparison test next. So the limit comparison test says to suppose a sub n and b sub n are series with positive terms. Okay, where again, a sub n and b sub n, like every single term needs to be greater than or equal to 0. Okay, the limit comparison test says that if the limit as n goes to infinity of a sub n divided by b sub n, if that limit is equal to c, where c is a finite number and c is greater than 0, then either both series converge or both series diverge. Okay, and then something that you're going to take note of is when using the limit comparison test, it does not matter which series is our a sub n and which series is our b sub n. So when I work through the two examples with this, I will do one of the examples where the series that we are given is a sub n, and the series that we're going to pick to compare it to is going to be b sub n. The second example, I will use the given series as my b sub n, and the series that I'm going to compare it to, I'm going to make that be my a sub n, and show that it works either way. Okay, so we're going to do two examples here where the directions ask us to test the series for convergence or divergence. And for number 1, we have the sum from 1 to infinity of 2n squared plus 3n over the square root of 5 plus n raised to the 5th power. Okay, so every single term in that series is going to be greater than or equal to 0, so we can use the limit comparison test. So as I mentioned, I'm going to make, for this example, our given series be a sub n, and then I want to pick a b sub n that I'm going to compare to a sub n. And the b sub n that we select, again, needs to be a series that we can show converges or diverges, usually by the p-series test or the geometric series test. So the way that we're going to make our selection for b sub n in this case is I want to look at what the end behavior for our formula is in our given series. So the end behavior for that formula is going to be dictated by the highest degree term in both the numerator and denominator. Okay, so the highest degree term up top is 2n squared. The highest degree term on bottom is going to be the square root of n to the 5th power, so I can write that as n to the 5/2 power. And then whenever I use my laws of exponents, when I'm dividing two exponents that share the same base, I can subtract their power, so that's going to be 2 times n raised to the 2 minus 5/2 power, which is 2n to the negative 1/2 power, which I can rewrite that as 2 over n to the 1/2 power. Okay, and I'm going to make